Our goal in this work is to enable end-to-end training of navigation policies for ground robots that can generalize broadly to a wide range of environments and follow reasonable conventions such as staying on paths and avoiding collisions. This requires large amounts of training data, which we can obtain from passive data, including from crowdsourced human teleoperation and action-free in-the-wild video. While these passive data sources can provide large amounts of data, this data lacks actions or only provides low-quality action labels due to non-expert teleoperation. To address this, we propose model-based reannotation to relabel data. Using the reannotated actions instead of the noisy actions allows us to successfully learn a more challenging long-horizon navigation policy, LogoNav. Our trained policies are deployed and evaluated on robots around the world, demonstrating well-generalized performance. To start, we apply the extended Kalman filter to denoise the action commands in the noisy dataset. We also prepare small publicly available navigation datasets with accurate action labels as a starting point for predicting actions. Filtering the dataset is not enough to mitigate noise, so we train a reannotation model with model-based learning. Since model-based learning is robust for noisy data, we can incorporate both the accurate GNM dataset and the large but noisy Photobot 2K dataset to learn a reannotation model. Since this model learns to predict actions between close image frames, we can directly use this model as a short horizon goal image condition navigation policy. Then, we use the reannotation policy to create more useful action labels for trajectories in the large dataset. We use this data to train the long horizon navigation policy, which can navigate the robot towards the goal pose about 50 meters away. We evaluate the trained policies in 6 different countries on different continents, succeeding in 96% of our trials in short horizon navigation and achieving 40% better goal-reaching performance than the baseline in long horizon navigation. For long horizon navigation, we feed the 2D goal pose and the first-person camera observations to guide the robot toward the goal. Here is a video of our long horizon navigation policy trained with model-based reannotation, where the goal is the red marker. As you can see, our policy allows us to keep traveling on the road with minimal disturbances and successfully arrive at the goal pose at the end of the path. In this video, we deploy the strongest baseline policy trained on the filtered action labels by the extended Kalman filter. The baseline does not take a sharp turn left to stay on the road and instead tries to take a shortcut through the grass. This policy does not end up reaching the goal, goes into the bushes, and we terminate navigation. Our 2D goals can be composed together to achieve longer trajectories. In this example, we use 4 sub-goals to navigate to the final position 340 meters away. The robot takes a smooth and safe path to intermediate sub-goals, reaching each one on its way. The robot travels without collision on both the road and the grass, ultimately reaching the far goal pose. We also deploy our long horizon navigation policy in difficult human-occupied space. Our policy enables the robot to prevent collisions with both obstacles and pedestrians. Even in a busy walkway, our robot tries to find the open areas to move towards the goal pose and finally arrives at the far goal position. To evaluate generalization, we deploy our policy on a quadruped robot with a different camera. Although there is no training data with the quadruped robot, our policy shows strong cross-embodiment performance. Our robot can keep traveling on a road without moving into a grass area. Our robot avoids collision and moves towards the goal position, even in novel environments. Here's our policy on another robot platform. Our policy works without any adaptation and shows strong generalization performance. We can also deploy our reannotator as a short horizon navigation policy, which uses topological memory. Our policy generates the proper action commands to move toward the goal location, and our robot can arrive at the final goal pose by updating the goal image. When the baseline trained with imitation learning attempts the same trajectory, it fails. highlighting that imitation learning is subpar to train on noisy data. In this trajectory, model-based reannotation once again reaches a short horizon goal, which demonstrates robust performance.